Here's some stuff on testing continuity for piecewise functions. And let me a little context here. At this point, you want to know that we have a general theorem on our standard library functions and the fact that they are continuous at every point in their natural domain. So certainly things like polynomials, the exponential function, sine and cosine, but even things like tangent and secant, things that actually do have some nasty points, but we already know they're nasty because those functions are not defined at those points. So for example, tangent of pi over 2 is not defined, so we wouldn't expect it to be continuous there. And in fact, it has an asymptote. But we've got something that says that as long as we're working with standard library functions, and then we put them together with nice operations like addition and multiplication, we're just not going to expect discontinuities. This is a nice fat feature of the functions we have to work with. So when really should we expect discontinuities? Well, first of all, at a point where that's not in the domain of the function, certainly in anything like an asymptote. But a particularly common cause for discontinuities is if you have a function defined as a piecewise function. Then the situation flips, and it's actually rather it's a little bit of a challenge, and you have to actually carefully design a piecewise function usually to make it continuous, because you're going to have two pieces that need to match up. So let's do a particular example of that. A few examples. So number one is going to be f of x is evaluating cosine x, let's say if x is less than or equal to 0, and x if x is greater than 0. And I'd like to know where is this continuous. In light of this big theorem, though, that library functions are continuous, as long as we're away from the breakpoint here, we can just say this is going to be continuous. So it's really more about, we can focus on where is it discontinuous. And the only point where it could possibly be discontinuous is at that breakpoint. So let's sketch it and just get an idea of, okay, is it actually discontinuous there, or are we going to get lucky and have it be continuous? Oh, I probably shouldn't have erased the definition. Let's put it back up here. But it's pretty simple. Cosine x or x. Okay, let's just save that. Okay, so it comes in being cosine x to the left, just very quick and dirty graph, and then x. Now, when you were first taught to graph piecewise functions, most likely, you were taught to include either an open circle, at a breakpoint like this, you were taught to either include like an open circle or a closed circle as like the end of the curve, depending on who got the value. Let's make this a little bit better. In this case, it's cosine x that gets evaluated at x equals 0. That gives you 1, and so you do a closed circle there. And then we put an open circle down here. Now, what is that open circle actually denoting? And that's something that people don't get a very precise explanation of what that open circle actually really means in a graph of a piecewise function. That's absolutely a limit value. And I talk about this in some other videos. That open circle is absolutely not f of 0, but it is an explicit indicator of what the limit from the right of f of x is. So that is exactly saying the limit as x goes to 0 from the right, 0 plus, should be the height of that open circle, which is 0. So when you draw an open circle, you're really saying that's a limit value, and usually a one-sided limit, but sometimes two-sided. Okay, so from almost any intuitive understanding of continuity, just immediately visually from this graph, you can see that it's discontinuous at 0. It's got to jump. That's one way to say it. You cannot draw it without lifting the pen off the paper. But let's go ahead and really carefully use the limit definition of continuity to ascertain that. Let's see if I can squeeze it in over here. I don't know. Okay. So what's the definition of continuity? Whether it's continuous at 0 is going to be, does the limit exist, and is it equal to, and does the value exist, and does it equal to the value? And we have to get even a little bit more explicit, because this is a piecewise function. and we're at a breakpoint, we're going to evaluate that limit by splitting it up into the two one-sided limits. And that's really the main point as to why this is going to be discontinuous, is those two one-sided limits won't match. So we're going to take the limit as x goes to 0 from the left of f of x. And notice right off the bat, I'm just saying the limit of f of x. I'm not plugging this in right away, because we have to start with it's f that we are taking the limit of. But the next thing is we then go to say, the actual calculational procedure, the formula for f of x. When x is coming in from the left, we can make that more explicit. I don't change this at all. It's still the limit as x goes to 0 from below, from the left, whatever you want to say, of this function, because that is the only thing I ever evaluate when x is a negative number. Okay, and that, now cosine x, if this were in isolation, like if it were just going on like this, that is continuous. And the great thing about continuous functions, one way to say it's a continuous function, is it's got the plug-in property. A limit is the same as if you just plug in the target into the function. So that's just cosine of 0, and that's equal to 1. Okay. And so there's a really important two-stage process. I didn't say f is continuous, boom, it's equal to 1, because it's not going to be continuous. But I said, when I look at only one side of this limit, just temporarily only looking at negative values of x, f is behaving exactly like cosine, sort of as if it continued in this dotted line. Well, of course, that's going to be cosine of 0, and that's 1. Okay? So, similarly, on the other side, limit as x goes to 0 from the right of f of x. Okay, that's not continuous. I can't just plug in. But I can take advantage of the fact that I'm only looking at positive values of x. And that's going to be the same as if I took the limit as x goes to 0 from the right of x. There's that open circle value, advertising, that if this were the only function I was cared about, f of x, that would be 0. So again, this is a continuous function on its own terms. And I can just plug in the 0, and I get 0. Okay, so now just ignore how we got those and just advertise to somebody, hey, look, this is a function whose left-hand limit is 1, whose right-hand limit is 0, which hopefully should be clear from the picture. Those limits are not equal. We're done. There's nothing else we need to say to show that this is discontinuous. So let me just summarize that here. Left and right-hand limits are unequal. And so the full limit does not exist, and therefore the function is discontinuous at that point, and only at that point. It's the only place where it had any chance of being bad, and it's discontinuous at that point. Okay. All right, so we'll do some more examples in a couple of other parts.